No, so this is your first one here?
Yeah.
Okay. Students from... for this week's CERIAS Security Seminar, our speaker today.
I don't think the mic is on.
Hello and welcome to the CERIAS Security Seminar at Purdue University. Our speaker today is a PhD student in computer science here at Purdue, Koray Mancuhan. Koray?
Hello, everyone. Welcome to my talk. So, as Joe said, I'm a PhD student in the Department of Computer Science, and I'm also a member of CERIAS. And today I will give a talk about data privacy and anonymized data. So here's the plan of my talk. So first I will talk about why we need data privacy in today's world, and then I will give a brief summary of some of the common data privacy standards. And then I will continue to my talk by giving some of the data anonymization techniques. And then I will give two examples, if we have enough time, of anonymization applications like querying anonymized data or mining anonymized data. And then I will give a brief conclusion by outlining what kind of concepts I talked to you about today and what to keep in mind. So I hope things will be more clear in the end of this talk about the field. So let's start. So why do we need anonymized data? So as probably you know, in today's world, data sharing is very common. And there are many examples of it. I mean, cloud computing is just one very common example. Even in my daily life, I prepared these slides and I stored it in the cloud using Dropbox. And so we all provide some data, some sort of, to the third parties in today's world. But we don't know what kind of things they can do with the data that we provide to them. And especially after 2010, with the rise of internet and social network, especially with Facebook and Twitter, there are too many sources of information on the web about us or anyone. So, and these kinds of issues, sharing the data to the third parties and the rise of social network, they cause us privacy concerns. So I will just give two examples of what kind of concerns I'm talking about. So the first example is from 2002. And in 2002, we know that there was no Facebook, no Twitter. There was just MSN Messenger, and cloud computing wasn't even a big trend. And in 2002, Laura Sweeney was able to identify from the publicly available medical records the governor of Massachusetts, and she was able to find his medical condition from the publicly available data just using an external data that she purchased for $20 for voting, so public voting records. And she just used three pieces of information from the public voting records, just the age, the zip code, and gender of the governor. And she mentions that 87% of the US population is actually unique, using just age, zip code, and gender information. And using these, she says that, like I did for governor of Massachusetts, everyone can be identified with a little bit effort. And in 2011, of course, it's impossible to avoid a Facebook example in a data privacy talk. So Facebook is known selling all of our users' information to the advertisers and to any app developers. And even they are known to sell our home addresses or phone numbers if we provide them to the third-party websites such as Yelp to provide better services. And these two examples show us that there is a concern, but saying that we cannot share any kind of data is really not realistic in this world, in today's world, because we love the convenience of it. It's in our lives. And since it's not realistic, we in US government, I mean, there are also European regulations about it, but US government introduced after 2000s 2 regulations. So I just picked here HIPAA, which is one of the first ones about Healthcare Insurance Portability and Accountability Act. And we also have the Children's Online Privacy Protection Act, which was introduced in 2013 by Federal Trade Commission. So in general, I will just give an example from HIPAA, and if you see the material in the literature, they all mention this, but it's very important. So why do we worry about the shared data? Because even the regulations say the beneficial usage of the data is more important than just identifying the peoples itself. So what in concrete example, it's okay to identify the governor of Massachusetts in the previous example that I've just given, but they say if the medical records can be used to improve, to provide better services and medical treatments to the patients, then it's okay just sharing the data in some sense. But here, they also force that there should be some precautions to avoid some level of identification. And what I would tell is that this brings us to the purpose of this talk. So we want to make data as much as useful as possible. So it should be useful, it should be beneficial, but we should minimize the personal identification. So these introduces the data privacy standards that CS major came up, CS researchers came up, and also brings us to the anonymized data and data anonymization techniques. So now I will talk about data privacy standards. I won't be able to give you all the standards here, obviously, but I will just give you a brief summary, and I will just outline the 2 of them. The ones that I will talk about here today requires the concept of attribute division. So Laura Sivini, who did this work with the publicly available Massachusetts medical records, she essentially grouped attributes into 3 groups. And the first group that she made is the identifier attributes. So she says that if we have a data table A to anonymize, we always have first identifier attributes. So these are the attributes that you can use to identify anyone. So it's like social security number, first name, last name, taxpayer ID, this kind of information. So you don't need another data table to identify people. And the second group of attributes that she mentions are the quasi-identifier attributes. So they have still powerful identification properties given another table. So if we go to the original example that I gave in the beginning, so the information that she used for public voters registration list is the additional data table B, and she can use it as in the literature they say it as background knowledge. So she can use it to identify precisely one person, the governor. And some examples are zip code, birth date, and gender. And the last group is the sensitive attributes. So basically we just don't want people to know what these attribute values are for a given individual. They can be gender orientation, they can be medical condition, and so on and so on. So the first standard that I will talk about is k-anonymity. So basically what it says is that we have a bunch of quasi-identifier attributes. Let's say that those combination of values for each quasi-identifier attributes record in a data table. Let's say that those records, they occur at least k times. So the basic idea of it is that you cannot identify specifically a data record. So in this example, this is the one that I retrieved from Laura Svini's paper. So you can notice that she uses as case identifier attributes like race, birth, gender, and zip. And the medical problem is the sensitive attribute. So what she says is that this is an example of K anonymous, 2 anonymous data set. So K is equal to 2 here. And if you look at this table in detail, you will see that every record, there is at least one more record which has the same values in the race, birth, gender, and zip values. So if you look at the first record, the person who is black, who was born in 1965, who has a gender male, and who lives in the region 0214 star. I will talk about star more later, so don't worry about it. So you will notice that the second record is exactly the same as the first record. So there are 2 of values like that. So she claims that since we cannot identify specifically which record belongs to which person, we don't know what the sensitive attribute is, and everything is good. But then this new idea in 2006 rises. So it's called L diversity, and it's another data privacy standard. So they say that K anonymity is actually not enough. And you can see it in this 4 anonymous data. And if you look at the records from 9 to 12, you will notice that the data is 4 anonymous, so we cannot identify, even with another data table, which record belongs to which specific person. But we know that all the records from 9 to 12, they have the sensitive attribute cancer. So even though we cannot identify precisely the person, we know for sure his or her medical condition. So it really doesn't matter unless you assure the diversity of the sensitive attributes. That's what they exactly say. And they define the idea of L diversity. So from the previous example, this data table has exactly 3 groups or blocks. Some people call it blocks, some people call it groups. I prefer calling it groups, but so this data table has just 3 groups, and each group has 4 records. And they say that a data table A to anonymize is composed of such groups, and the group Q has at least K records. So in the previous example, it has at least 4 records. And what L diversity says is that each group in this data table should have at least L different sensitive attribute values. So if we go to the next slide, you will see that the way that the records are ordered in the table is totally changed. So it's not consecutive anymore. And we can see that this is still a 4 anonymous table. So every group is composed of 4 records, and they are all generalized. So we still can't identify precisely a person. But you can see that everyone has 1/3 chance, 1/L chance of having a specific medical condition. So you can see that no one has cancer for sure. And another privacy standard is differential privacy. So I won't talk a lot about this. So this is also introduced in 2006 by Cynthia DeWerk, and you can see her work. But I will just say that it's a breakthrough because it just assumes that there is no separation in the groups of attributes. So what she says is that it's not meaningful to separating them, and she shows theoretically that perfect privacy is impossible anyway if we want to provide to the people some usefulness in the data. But it has some issues with certain applications such as text, etc. I won't elaborate a lot. So in the audience, I have a colleague, Bala, who will elaborate about this more in 2 weeks. So I think it's a topic which requires a special session just on it. So I will just skip it. And I can also mention some other privacy standards that I will skim through quickly. And I'm proud to say that Purdue is quite active in defining privacy standards, especially another CERIAS member, Professor Ninguli. He has been working a lot on T-closeness and other types of L diversity that I will talk later. And you can also check out other extensions of K-anonymity called alpha K-anonymity. So basically, all of these standards, they are defined based on some vulnerabilities that people defined over the last 10 years from early 2000s. And every one of them tried to handle one flaw that they noticed. But apart from the privacy standards, one last thing to talk about is, of course, secure multi-party computation. And my advisor, Chris Clifton, has a lot of work about it. And my colleague here, Bala, again, he has some published work about it. So he will also emphasize in his talk more about this field. So I will also skip that. So now I will just talk about the data anonymization techniques. So the data anonymization techniques, so I defined why we need data privacy, why we need, and I also talked about some data privacy standards. So obviously now I'm talking about data anonymization techniques. So data anonymization techniques, they are just some stuff which makes sure that when we release the data table A, in my example, it satisfies certain data privacy standards, such as K-anonymity or L diversity. So I will talk about two data anonymization techniques. So the first one is going to be about K-anonymity, and the second one will be about L diversity. So the first one is generalization and suppression. So it's also introduced by Laura Svini in 2002, right after K-anonymity. So basically she says that we can make people unidentifiable in the table by just generalization of the values. What do we mean by generalization? It's just replacement of a value with a less specific value. If you have a numeric value, such as zip code like 02138, you just replace the last digit by a star character. And if you have a little bit different values, like discrete values like Asian, white, black, you just replace it as person. And suppression is just replacing the values with a generic value using star sign. And I should note that in this idea, every value is generalized in the end to all stars. So you just replace it with something empty. And in the generalization, there is always a hierarchy. We call it DGH and VGH, so it's domain generalization hierarchy and value generalization hierarchy. So I will explain you more about it. So these are two examples of that kind of hierarchies. So you can notice that the first one is about zip code, and the value generalization hierarchy is just a tree. It's basically a tree with values on the leaf as the specific attribute values. And if you go from leaf to the root of the tree, at every level, every depth, every height of the tree, you have somehow a generalized value. And at the root, we have the suppressed maximum, as I just said. So it's just stars all over. And it's the same if you don't have a numeric value. It's a bit different in the sense that you can see in the race hierarchy. So it's just generalized to person, the specific race values. Of course, these are just two examples. So you can just make it as big as you want, the trees. It depends on how you define them. And if you notice it on the left side, we have the domain generalization hierarchies. So basically, if you look at the tree and the tree one and the set one, they are in the same line, all parallel. They just have the same values. So domain generalization hierarchy is just another way of writing the same information, same thing. So she defined an algorithm. I won't elaborate a lot about the algorithm. So I will just give a sketch of it. So it's just a 3-step algorithm. So obviously she wants to make as minimum as possible the generalization operation. And for that, she defines a precision measure. So what precision measures is that how much do we do the generalization across all the cell values in a data table. So if we have maximal, like if the precision measure becomes big, it means that we didn't generalize a lot. And if we have a small precision measure value, it means that we generalized a lot. So few generalization, high precision value, low generalization, low precision value. And what she does is that she takes the data table A to anonymize, and then she creates all possible generalized tables from it. It includes even the tables with all suppressed maximal, all star values around. And then among them, she picks the ones which satisfies the k-anonymity ones, the k-anonymity standard. And then in the final step, she just picks the table which has the maximal precision value. And the second data anonymization technique is anatomy. I could have given the same idea that the folks who introduced the L diversity first used, but I changed a little bit the anonymization standard here. So this is another anonymization standard called anatomy. So what it does is that it's also introduced in 2006, right after the introduction of L diversity. So what it does is that it just divides a data table. So in this example, we have a data table of 8 records, and the data table has attributes age, sex, and zip code, which can be used as case identifiers, and the sensitive attribute disease. So what they do is that let's separate age, sex, and zip code and the disease and put them in separate tables, and let's make sure that every record in the table which contains the age, sex, and zip code, it should match to the L potential diseases in the other data table, in the L potential records in the other table, which contains the disease. And this is just the example, the result of that kind of operation. So you can see that the first record, who has the age 23 and who is male and who lives in 11K zone, he can only have 2 medical conditions, either dyspepsia and pneumonia. And if you check the other records in this data table, you will see the similar behavior about them. So, and it has an algorithm called bucketization. So what it does is that it just takes the original data table, in this example the disease, in step 1, it puts all the records in a hash table with buckets, and each bucket contains the records belonging to a specific disease type, in this case, sensitive attributes. So pneumonia diseases, so the record number 1 and the record number 4 are put in the same bucket, and then the record 5 and the record 7 who have flu, they are put in the same bucket, and it just goes on like that. So it creates the buckets, and then in the step 2, it just, from these buckets, it picks, according to the given L, it just picks the L number of records, and when it picks, it just picks one random record in each bucket. And in the end, there will be some remaining buckets. There will be less than L. So if we have like 4 diverse data, if we want to do a 4 diverse data, in the end of this algorithm, we will have 3 buckets, 3 or 2 buckets, depending on what kind of distribution we have. And it just assigns the remaining tuples into the existing groups, and then it just creates the separate tables from it. There are also other data anonymization techniques. There is a better k-anonymity algorithm, anonymization for k-anonymity, in 2006. You can also check the case for multiple sensitive attributes. There are also other improvements on anatomy by the faculty here again. by Ninguli and his students. And he also suggests the other idea that I mentioned in the beginning in 2012 for L diversity slicing. I won't elaborate about these two, but if you're interested, you can just visit his personal page and find one of these papers. So now I will just introduce some examples about data anonymization usage. So when and the examples that I will give, they are about how to query and store the anonymized data and how to mine the anonymized data. And each example will be belonging to a specific privacy standard. So obviously it will be either k-anonymity application or L diversity application. So the first example is about querying anonymized data. And I'm proud to say that this application was developed by a senior student in our lab in Purdue again, by Erhan Nergiz in 2011. And then he also has other work which was published in 2013. So I will just explain here briefly his first version. So his work's first version. So the first one is, so here he uses the anatomy model, and it's a little bit augmented version of it. So so this is an L diversity application, and it's a data outsourcing scenario. And as you can see, we have again a client which has some data and outsources to some server, which handles that kind of operation that I just defined: bucketization, tables, separation into tables, anonymization. And then after doing this kind of operation and some encryptions that I will just show, it just sends it to a third-party server to store it. And this database operation is defined for, this database is defined for operations in this schema. The operations are selection, insertion, and update operations. So I will just emphasize here the selection operation, and this is the idea, and this is the theory that he developed in 2011. In his 2013 work, you can also see insertion and update. So I will just now talk about the selection that he did, and I will just go through an example, and I will avoid any kind of theory that he did in that paper. So if you look at the query, we have a patient table, which you can see in the example below. Oh, first, I have to mention that if you noticed from the previous examples that I have given when in the first part of the talk, there are two additional fields in this separate tables. So they are called sequence numbers. So that was his idea of augmenting the original scheme. So what he did is that he just used a sequence number to identify which record in the first case identifier table, the table on the left, matches to the which record on the table on the right. So for example, if he wants to match the Eric with a specific medical condition, he knows that he has to decrypt the relevant records in the sensitive table, and after the decryption of the first attribute that I call H in the parentheses sequence, he obtains the precise value of the sequence numbers, and he notices that the second record, which has the medical disease fever, and the value, the first attribute value, H sub K2 in the parentheses 2, it has actually the sequence number 2 after the decryption of the H sub K2. So it matches Eric with age 22, who lives in Richmond, to the second record, which is the fever disease. So this is how he uses the selection operation. And the key idea that he uses here is that he says that the data publisher, the client, they don't have to do anything, everything about the query processing. So what he says is that if you look at the where condition in this query, there is age, which could be processed just on the table on the left. And then there is disease in the second condition within the parentheses, between two ends. So it's it's disease is equal to flu or disease is equal to cough. And you can see that it can be only processed on the second table, on the sensitive table. And you can see that the third condition is disease is equal to cough or address is equal to Lafayette. And you can see that these two conditions can also be executed separately on two different tables. So what he says is that given a data query on this canonical format, he just defines a way of splitting the queries into two tables in the third parties. So third parties run these individual queries on each specific data table, and then they just return the results based on the results the client is able to reassociate the right query answer. And the result of this query will return in the next slide, the first line. So after dividing this query on the top onto two tables, so you can just see that on the server we have two tables as a result of that selection operation splitting, and the left side is the result of the query on the case identifier table, and the right side is the result of the query on the sensitive table. And then client combines these two tables, and then after the decryption of the sequence numbers H sub K27 and H sub K28, it is able to match that Jason, who has age 47 and who lives in Lafayette. It can be matched to the disease cough, because as you can see, they have the same encrypted values. Actually, he used in his example the encrypted version, but yeah, the idea is the same. So this is one application of anatomy and L diversity standard. And I won't elaborate more about this. So I will more talk about the anonymization examples now. So, and I'm sorry, I will talk more about mining the anonymization, the anonymized data. And the first example is about k-anonymity, the generalization methods. And this idea is developed by Inan et al. In 2009. So basically he says that we want to classify a k-anonymous data, and we want to learn the sensitive attribute using the case identifier attributes in the k-anonymous data. And they do it for nearest neighbor and support vector machine algorithms. And the two key ideas here is, again, the first idea is again some kind of augmentation of the existing generalization. So if you look at the example here, you can see that in the data table, there are two attributes which are generalized. They are case identifiers. The attribute A sub 1 is the education, master's and senior section. And the second attribute is just age. So it is the generalized age between 35 and 37 and between 1 and 35. So they say that for every generalized record within a group, so there are two groups here, obviously. The first groups are from record 1 to 3, and the second group is from record 4 to 6. And you can see that for each attribute, it provides some statistics. So for example, in the first record, it says that for the first record, it has all the records in this group, they have the value masters. So it has a probability 1. So it's for sure that it will have the value masters. And for the second attribute, it just gives the average of the age values. So it just sums up 35 and 37 and other values. Actually the other values within that group. And then it just says that it just averages them. So it just divides them. And it provides the variance too. So it's again a bit augmentation of it. And the second idea is just using these augmentations to do some approximation for the vector operations over the records. So I won't elaborate more about this, but it's quite an interesting idea. And if you're interested, you can read his paper about it. And it's cited a lot. And in the last 15 minutes of my talk, I will more focus on what we have done here in Purdue in my lab. And I will talk about my work on classification trees. And it's also another application of data mining on anonymized data. But we have, in this case, anatomy. And it is, of course, the application of L diversity. It is a classification case on L diverse data. And we used here the augmented version of Erhan Nergiz, the previous database example. So the learning objective here was to predict a quasi-identifier attribute using the remaining quasi-identifier attributes and the sensitive attributes. So if we go back to the original example, let's say that I just want to predict a person's age using its zip code, occupation, etc., some kind of quasi-identifier attributes, and its medical condition. And I want to do it using the decision tree classification. And the key idea that I will talk about is the on-the-fly subtrees. So you will see soon what it is. But first, I want to give this diagram which outlines in a better way where my work stands. So if you look at it, the first part, which is about query processing, it's what Erhan did. So we have data publishers, clients. I will use here data publisher term in a more generic sense. And then we have the third parties which store the data. And we use anatomization. And then we use the SQL queries for selection, right, I just mentioned, to retrieve some data from the stored data on the third parties. And what I do is that I just suggest a decision tree learning algorithm, and I just say that let's make a collaboration for learning this model using the third party and the data publisher. And in this way, we can reduce the learning cost or the decision tree building cost on the data publisher. And we can also profit from the data, which is outsourced to the third party. Elaborating the idea of this collaboration, and of course, before elaborating the idea of collaborative decision trees and the thing that I just mentioned, on-the-fly subtrees, I want to just say, sorry, I want to just say that why don't we predict the sensitive attribute like they did in the Anonymized Data in 2009? We don't want to do it because in 2009, in the exactly same year, it has been shown that doing such an operation is computationally not tractable, and it requires enumeration of all possible combinations of the data table with the sensitive attributes. So in 2009, Kiefer shows that there are some approximation algorithms, but we just don't want to go into there. And the other thing is, apart from approximating, we just want to learn models without violating anyone's privacy. So we believe that there has been already a lot of effort in attempts to violating the privacy. And we know that the privacy regulations already say that as long as it requires us some usefulness in the data, it's not necessary to really achieve the improved privacy as much as possible. And there is already proof that the perfect privacy is also not possible. So we believe that it's not really important aspect to focus on. So the first thing is there are two naive approaches here that we can talk about. So the first one is let's leave all the learning and storage to third parties, and let's assume that data publisher doesn't do anything. And it's good in the sense that we don't have any cost for building the decision tree. And the second option is let's consider the sensitive attribute, but obviously the third party cannot associate it. So let's leave learning part of the decision tree, the building part of it, to the data publisher, and let's assume that the data storage is just left to the third parties. And in some sense, both of them might work in some scenarios, but they are not really good solutions. And why they're not is because number one, in the first option, we never use the sensitive attribute. So we don't know. So we waste the information which is released. And in the second option is that we use all the information, but we don't exploit from the third parties in any way to process building the decision tree. So unless we query what is the purpose of outsourcing them. So, and collaborative decision trees comes in the middle of both trade-offs. So, and from the name, you can guess that it's just a collaboration of data publisher and the third party for learning. So it just leaves storage to the third party, but in the learning part, in the building part of the decision tree, we say that we have two steps. So the first step is we just let third party learn the decision tree that we call base decision tree from the case identifier attributes such as age, gender, zip code, occupation. So these are the attributes that we use to learn some decision tree at the third parties. And we assume that they already have a class attribute. I mean the one that we predict for. So if we want to predict, let's say, the number of years they spend in the education, we assume that it's also part of the case identifier attributes. And in the second step, we say that data publisher can retrieve the specific descendants of this tree, the specific leaves of this tree, and then they just learn a little bit more small subtrees from these leaves. And the reason why we call this on the flies is because in step 2, we just don't let the data publisher do in the end right after the step 1. So the data publisher does it when it only needs it. So it's an amortization idea. So you will see a little bit more why we call it on the fly in the prediction case. So data publisher, when they make a prediction for a new record, so it involves learning subtrees too. So in the step 1, they just send some case identifier values like gender, age, zip code, occupation, and they just expect a relevant tree of the tree. They just expect as a response a relevant leaf of that tree, the base decision tree, which is learned at the third party. And in step 2, third party obviously sends back this relevant leaf. And then in the last step, what we do is that if we have such leaf, we just look at it. So if it points to a encrypted subtree, then we just decrypt it, and then we just find the relevant leaf of that subtree and just make a decision, make a prediction based on that. And if there is nothing else in this, if it doesn't point to any subtree like that, encrypted, we just learn and then encrypt and then send it back to the third party. And the reason why we call it on the fly in the previous slide is because let's say that we made 100 predictions, and in all 100 of them we visit the first leaf. So at the first prediction we learn the leaf, we learn the subtree on that leaf, we just encrypt it and send it back to the third parties, and in all 99 remaining cases we just retrieve the leaf, and then we decrypt the pointing subtree, and then we just make the prediction from it. So if the 101st record, visits the second leaf, and then it's again a learning phase. So they learn again a new subtree, and it just goes on. So this is the basic idea. So we used some experiments obviously about it, and we used some open source libraries to implement it. So I won't elaborate a lot about how we evaluated it, but we just used the University of California Irvine collection. Probably as you are relevant to the information security, probably you heard about that collection and the adult data set from it. It's used a lot in any kind of data privacy application and analysis. And there are also other cases of other sets that I used here, but they are much more smaller than the adult data set. So, and obviously it depends on what kind of sensitive attribute we use. So anyway, so we did a tenfold cross-validation here, and we also considered the sensitive attribute and how it would change the resulting decision trees here. So if you would like to learn more, you can just ask me after the presentation, and I can just give you a pointer for my paper. So, and these are some, and this is just, and obviously to evaluate it, we just measure the execution times that client would do, and we just compare the accuracies between different tree types of decision trees. So yeah. So these are just the graphs which gives the results that we measured. So what we can say is that we managed to save a lot of time with reasonably good accuracies on large data set like adult. Those are the ones that you can see in the graphs in the last two options. Like in the last ones, there are 5 potential rows in this graph. So they are the last two ones. And we tried different options of sensitive attribute for this large data set, and it doesn't change a lot. I didn't explain a lot how I draw these graphs, so I will skip through this part a bit because we are coming to the end of our time. So I will just briefly mention what we did after the decision trees. So in the decision trees, we were able to obtain reasonable results, but it is hard to justify them theoretically because most of the time we know that we like decision trees as computer science perspective because it just works. It just splits things and we can just make predictions on them based on the paths that they follow. But the thing is, there are also other pattern recognition or prediction methods. They are some of them are nearest neighbor and support vector machine. So I can say that currently I theoretically show that it's possible to have a nearest neighbor classification, and it's possible to have some convergence on this type of data on anatomy, but it slows down a little bit the performance of it. So it increases the execution time and of course the error rate. So we are still doing some experiments on it, so I don't have any solid result about it yet. And we are planning to extend it to support vector machines too. And obviously we would like to see what would it do between this option of L diversity versus the k-anonymity version of these classifiers that Inan et al. Presented in 2009. So in conclusion, I gave a fast and a brief summary about privacy standards. So we have to keep in mind two standards here, key anonymity and L diversity. And then I talked about the common anonymization techniques, generalization and anatomy, which lets us achieve these privacy standards. And then I gave an example of an application using query processing. And then I gave data mining applications, one for each, for key anonymity and L diversity. And I outlined my research idea about L diversity. So I'm glad to hear your questions, if you have any, in the end of this talk. I think we run out of time, so it is 5:20. So, do you have any questions or any interest? If you have some, I had to go through it very fast because it's a big field, and it has been worked on since 2000s. So we are talking about at least 15 years of work, just alone, for the recent examples. So, and I even had to omit some of the stuff that people even developed in the 70s and 80s, and even before 2000s. So, yeah, thank you very much for listening, and I hope it would be helpful to you to give some directions, and I'm glad for giving this talk. Thank you. Yeah. So, yeah.